Hey everybody, so welcome back. Today I wanted to talk about asymptotes. I was specifically asked if I could talk about this topic, and I think it is a good one to talk to you about. Um, it's one that generally comes up in Algebra 2 in the sense of trying to figure out what they are. So Algebra 1, or college algebra, depending on when you're watching this video, will talk about rational functions and they'll talk about them in the sense that they have a vertical asymptote and a horizontal asymptote, but they don't generally get into what or why they're caused and where to predict before you graph it that you will find them. Um, and we always do this, at least as far as the algebra is concerned, in the context of rational functions. Now, a rational function is a lot like a rational number. Now, if you remember your numbers, a rational number is a number that can be expressed as a fraction where the denominator is not equal to 0. That's a rational number. Rational from the sense of ratio, where it's a comparison of two numbers, specifically a fraction, which is a ratio of part to whole. Now, a rational function is the same way. It's just one that has variables on it, and it takes a single input and it produces a single output within the domain and range. So when you look at rational functions, you need to look at the base function. So every type of function has its base function. For linear functions, it's y equals x. For quadratics, the base is y equals x squared. For rational functions, the base function is y equals 1 over x. This is the basis under which all rational functions can be assumed. So let me graph this, and we're using Desmos here, which you can always find at desmos.com/calculator. I'm not pitching an ad for them, I'm just using them. So y equals 1 over x. Now we go to graph it. Here, let me put this in projector mode so that the numbers are easier to see. So we see that we have this L-looking curve on the top right in quadrant 1, and we have this 7-looking curve in the bottom left quadrant, quadrant 3. And if we want to analyze this, we can look at the numbers. Remember, the x values go from left to right. Now, if we take an x value and we plug in a number, we're going to get a smaller and smaller fraction. So I want to put in here a and 1 over a, where we can have a be a number that we can manipulate. So as we get further to the right here, we start going down. 1 over 8 as a decimal is 1.25, or 0.125, I'm sorry, 0.125, which is very small, is really close to 0. And the bigger these denominator numbers get, the smaller the fraction gets. Now, it's never going to go below 0, because in order to get a negative number, you have to start with a negative number. And because 1 is positive and our x values, our a numbers, are positive, it's always going to be positive divided by positive. You're never going to get a negative number. The thing is, no matter how big this a gets, you're never ever going to go to 0. If you go out to a billion, then you're going to have 1 over a billion, which is going to be 0.8 zeros and then a 1. So you're going to get close and close. And now we can go arbitrarily far out until as big a number as we want. And the decimal that we get is going to get arbitrarily smaller. But as close as you can get, it's never actually going to touch. And so we'd say that as x goes out to infinity, remember infinity is not a number, as x goes out to infinity, the y value gets closer and closer to 0. And then the same thing for negative infinity, because if our x values are negative, we're going to have 1 divided by a negative number, which is going to be negative. And as the x number gets more and more negative, that fraction is going to get closer and closer to 0. Now it's going to be a negative really close to 0, which is why it's on the bottom side of this line. So as we get closer and closer, or as we get further and further out to infinity, this y value gets closer and closer to 0. So because this is never going to touch 0, not on either side, we would call this an asymptote, and the asymptote would be located at y equals 0 because that is the value it can never be. Change this to change it to black and make it dotted. We have an asymptote here because no matter how far we go in this direction, no matter how far we go in this direction, it will never be that value. Now it's beyond the scope of this video, but there's another type of value that the function can never be, and that's called a discontinuity. We don't deal with those here, not in this video. You sometimes deal with them in Algebra 2, more often in pre-cal. Definitely by the time you get to calculus, you'll talk about discontinuities. But there's another kind called discontinuity, and it is related but different. And so I won't talk about it. Like I said, it's beyond the scope of this video. Now, looking at this graph again, you'll notice that as we get closer and closer to 0, you'll see that these numbers get bigger and bigger. Well, it's the opposite effect here. At 1, you've got a point here called 1, 1. Oh, I probably shouldn't have done that. You got a point here, 1, 1, that's right on that graph. That point is right there on that graph. As x is between 0 and 1, it's a fraction. Now, what happens if you have a fraction over a fraction? The fraction is the same as division, so this is really 1 divided by 1/2, copy, dot, flip, 2 over 1. 1 times 2 is 2 over 1, and that's just 2. So at 1/2, the y value is 2. As this fraction gets smaller and smaller, we have the reverse effect that we had up here, or that we had over here. And the y values are getting bigger and bigger as the x gets closer and closer to 0. So as you get closer and closer to 0, y is going to shoot up. It's never actually going to touch. Think of it as like getting close and slipping. And then the same effect on the negative. As you get closer and closer to 0 on the negative side, then this number is going to get closer and closer to, or get bigger and bigger on the negative side out toward negative infinity. And so x can never be 0 either. So we've got another asymptote here. Let me get rid of these points. We've got another asymptote at x equals 0. Why x equals 0? Because that's the value it can never be. So the idea here that x cannot be 0, it is very much related to this idea that b can't be 0 in rational numbers. The idea behind this is you're trying to divide this number into this many parts. So let's say you've got 1 over 0. How can you divide one thing into 0 parts? It doesn't make any sense. There's nothing to put the 1 into, and the 1 can't go anywhere. So this number doesn't make sense, so we don't allow it. It's the same thing right here. If we allowed x to be 0, then we'd have the same effect, and we're saying one thing going into 0 parts. So we always say that the denominator cannot be 0, and it's because of this asymptote. Now, if you want to get technical, we could rearrange this. Remember our cross multiplication properties. Well, Mr. Pledger, couldn't you say that if we use our multiplication properties, x equals 1 over y, couldn't you say that y can't be 0 either? Yes. The answer's a little more complicated than that as to why y equals 0 is an asymptote, but breaking it down, that's not a bad approximation of the reason. So now we start with this base function, y equals 1 over x, and we wind up with two asymptotes. The only catch is that we can start moving this around. We have these not transpositions. I'll think of the word. But we can move this left and right, translate it. We can translate it left and right. We can translate it up and down. And if our number here, if this was instead of 1, let's say this was 2, we can raise the magnitude of this, and we can make it bigger or we can make it smaller, just as long as that number doesn't get to 0. Because you can't, if you have 0 over x, then you just wind up with 0, and that's not a rational function. That's just a constant function. So we can move it left or right, and we do that with the idea of x minus h, where h is how far you've moved it left and right. It's inverse to the number, which is why it's minus h. You can also subtract k from here, meaning that's how far you move it up and down. It's also inverse. And to be fair, most of them don't teach it this way because we like y by itself. We add it to both sides and leave the k there. Some people get confused as to why it's minus h but plus k. It doesn't matter to me, but I'm probably going to write it this way just so that you can get the idea that this h and this k is inverse. To remember which is h and which is k, just remember h goes to x because x is horizontal. And then k goes to y because y is vertical. If you want to think of the c in vertical as a k, I don't know, just remember it's the one that's not h. And then the amplitude up here we're going to call a. Now I'm not going to add these because I've already done it over here. And I have nice little sliders and everything. And you can see that as the amplitude goes up, then that stretches that way. As it goes negative, it goes the other way. As I get to 0, look what happens. You see the blue line on x equals, or on y equals 0. It's just a constant. It's not a rational function anymore. But as soon as you give it a decimal value, it becomes rational again. So it's not that a can't be 0, it's that a being 0 does not serve our purposes here, and so we're not going to consider it. So now that a value can be whatever you want. If I move this h value horizontally, notice I'm going to make this h value to be 1. The value moves to the right, or the value of that asymptote moves to the right to x equals h. That's what that asymptote is right there. X equals h. And the reason it's minus h is because you have to subtract h from every x value in the table before you can take its reciprocal for the function. If I have 1 over x minus 3, let's say, and I want to consider x equals 4, I have to subtract the 3 to get 1 before I can find its reciprocal of 1 over 1. And let me show you that. I'm going to make this 3 right here, and at at 4, my y value is at 1 because I subtracted 3 from the 4 before I took its reciprocal. The idea of subtracting the h and subtracting the k is in order to get it back to this base function. And the k is the same way. If I move this, let's say, down to -3, where y minus -3 is y plus 3, that's telling me for every y value, it's 3 higher or 3 lower than it would normally be. So if I took x equals 2, 1/2 is 1/4, or is 2, sorry. X equals 2 is 1/2. 1/2 minus 3 is 2.5. Oh, I'm on negative. I think I messed that up. Where am I for x equals 2? 2 is -4. Oh, you know why? Because I still have this 3 here. I messed myself up. So here at 2, it would normally be up here at 1/2. But because I got y minus 3, whatever it was, has to be 3 lower. See, you guys could have got 5 points off of me because of that. So the asymptotes here for your base function, where x minus h is in the denominator, you're going to wind up with an asymptote at x equals h. If you have a y minus k here, then you're going to wind up with an asymptote at y equals k, because the h and k are what are required to return it to this base function. I think I've repeated that like 4 times now. Sorry. So what about bigger ones? Because we can multiply times 1 over, and then instead of x minus h, we'll say x minus I. You know what, I should have probably done it back on this other one. Here, let's do that. Times 1 over x minus I. And I'll add a slider for I. Ooh, it got all weird on me. So here's my slider for I, and I'm going to move that down under h. So remember, X can't be H because that would make the denominator 0. And you can't have a denominator of 0. Similarly, X can't be I either because that would also make the denominator 0. We have something called the multiplicative property of 0, which says no matter how many things you're multiplying, if one of them is 0, then um, then your answer is going to be 0. If either of these denominators gets to be 0, then you're going to have an asymptote. So I'm going to have another asymptote at x equals I. Change that one to red and dotted. So now h equals 0, I equals 1. I have an asymptote at x equals 1, and I have another asymptote at x equals 0, x equals 1. Sorry, I get a little excited about this. If I change these numbers, then that gets bigger and smaller. Now I can do that as many times as I want, times 1 over x minus j. And I'll add a slider for j, and I'll add another asymptote for x equals j. Oops, j. Let me change that to red and lined, or red and dotted. So now we'll let h equal -2. We'll let I equal 2, and we'll let j equal 4. Notice what this is doing. Every time we add a new denominator, we add a new asymptote here. The only catch is that all of these have to be multiplied because of that multiplicative property of 0. Another feature, notice that every time you go to 1, it switches. Now this one goes down and it switches that way. This one goes up and it switches to bottom. Now, I'm not going to give you a predictive analogy or a predictive algorithm for how to know which is which other than plug in a big number like 10, see whether it's above or below, and then keep in mind it's never going to cross and it has to switch. So that's the only predictive thing I can give you there. Pick a number close enough and see where it is. But the main takeaway here is these all have to be multiplied. So now how does that help you for this one? Let's say y equal, or y minus 3 equals, let me get rid of these. Y minus 3 equals 3, or make it 4, over x squared minus x minus 2. Ooh, how did we get that? So the catch is this is quadratic, but it's factorable. It has two real number solutions. If I factor x squared minus x minus 2, x and x, 2 is going to be 2 times 1. This is negative, so the negative goes on the 2 and the plus goes on the 1. So these are my two factors. So literally, I am the same as y minus 3 equals 4 over, and then in the denominator, x minus 2, x minus 1. Or x plus 1, sorry. Plus 1. See? One over top of the other. So by factoring it, I found this, and now I just have to say my asymptotes are going to be at x equals 2, because 2 minus 2 is 0, x equals -1, because -1 plus 1 equals 0, and y equals 3, because 3 minus 3 is 0. The takeaways. When is x going to equal 0 in the denominator? So x equals 0 in denominator. Y equals 0 by itself. So what number of y will turn this into 0? What values of x will make the denominator 0? I hope that helped everybody. It's been kind of a long video, and I know I repeated myself a couple times. Ooh, 26 minutes. So if you stuck with it, I appreciate you. Come back next time, and I'll try to make it a little bit shorter. Hopefully you guys understood. If you got a video that you want to see, let me know in the comments, and I'll try to make one for you, okay? Thank you. Have a good day.